Alright, so this is going to be the last class, and here we would like to make you understand what is called SVD. Singular value decomposition. So it is a decomposition, but you have to say what are called singular values for us. That I will have to explain to you. Fine. And this is the most important thing that we have, in the sense that starting with a matrix A, we had given you LU decomposition, that was for a square matrix, and from there we got the linear form also, that LU in some sense upper triangular form, so it was M cross N. We also have the notion of A is equal to BC, rank factorization, all right. Then A equal to QR was there, fine, where Q was such that Q transpose Q was an identity matrix of rank R, whatever the rank of the matrix is. Everything was dependent on the rank. Then given a square matrix this, we could say that, means we wanted to understand this as SD S inverse. So S is already non-singular for you, and D is the matrix of eigenvalues of A. This is not always possible. Sometimes you could do, sometimes you could not do, fine. Then we went to what is the Schur's theorem, which we said that there exists a unitary matrix U such that A is U T U transpose, and this T is upper triangular, fine, we could do this. This was possible for everything. From there at the next stage we went to matrix A, which is again this is a square matrix, and we assume that A is normal, and in this case we could show that I can write A as U D U star. I should have written a star here also in place of transpose, because I am looking at over complex numbers here. So A is U D U star for us, fine. So D is diagonal here again. So when A is not normal, I cannot guarantee that this upper triangular matrix has to be a diagonal, all right. So cannot guarantee T to be diagonal. Is that okay? That I cannot guarantee. But when it is normal, then I could go do it, fine. Now, so everything here that I have done till now in some sense is related with what are called square matrices. Here it was allowed to be M cross N, here also M cross N, M cross N. I could talk of this, but not understand much. And what we have seen is that understanding eigenvalues, eigenvectors are most important as far as our calculations and things are concerned. That is the application, because we only look at certain directions in which we want to maximize or minimize. We do not want full information, because getting full information takes too much of time, all right, fine. Computationally it is almost impossible to get the full information. So whatever minimum information we have, we would like to get the best information which is in the direction of maximum or minimum optimizing things, fine. So we would like to formulate those ideas in terms of now A, which is an M cross N matrix, fine. So what this SVD theorem says, that any matrix A can be written as U sigma V transpose, I think. Yeah, so this is the note that I have. So A is this, where U is a unitary matrix, V is also unitary, and sigma consists of singular values of A. So what are singular values? I have not yet defined what are those singular values. I have to define that as well for you. Is that okay? So let us try to understand first what do I mean by saying that A is U sigma V transpose. So A is an M cross N matrix. So this U, which is a unitary matrix, it has to be M cross M, fine. Sigma has to be an M cross N matrix, and this V has to be N cross N, fine. Understand them nicely. I want A to be an M cross N matrix. So U has to be M cross M, V has to be N cross N, I do not have much choice, So, the middle thing that I have has to be m cross n, so that matrix multiplication makes sense. That is the first thing that we need to understand, that we cannot get away with that part. The next idea that we have here is, let us just multiply and see, because we know about n cross n matrix. How do you use this idea of n cross n matrix to get to an m cross n matrix? All right, fine. From where do I get u and v? That also has to be understood. And from where do I get sigma? What do I mean by singular values? So, we need to understand that also. Fine. So, let us do that one by one. So, let us compute what is A times A transpose. A times A transpose is nothing but we want to write u sigma v transpose. This is your A. A transpose will be transpose of this, so it will be v sigma transpose. All right. Look at nicely, u transpose for us, which will be equal to u sigma v transpose v sigma transpose u transpose. Now, V is an unitary matrix, orthogonal matrix, whatever you want to say. Let us say it for the time being unitary, because we would like to then build up on those ideas, fine. But what we know is that over complex numbers, everything is nice. We have eigenvalues, eigenvectors, and therefore, everything is nice. So, V is unitary for us. So, if I look at this here for the time being, I get here is it is u sigma sigma transpose u transpose. All right. This is more important for me. Understand this, that if I write this matrix as D, fine. If I write this matrix as D, I have got that A transpose as u d u transpose. Fine. Now, what is A transpose? Look at this matrix A transpose. Take the whole transpose of this. You get A transpose whole transpose and this, which is same as A transpose. So, a symmetric matrix. A symmetric matrix. That is one thing. I observe that this is a symmetric matrix. That is the first thing we observe. Now, what is D? D is sigma times sigma transpose. And what is this? Sigma is of the size m cross m. This is n cross m. So, I am getting a matrix of size m cross m, fine. So, keep track of things. A is also m cross n, this is n cross m. So, my everything is m cross m. So, what we are doing here is that in some sense I have got this matrix which is a symmetric matrix. I already wrote it is symmetric matrix, and then I am looking at the decomposition of A transpose in terms of eigenvalues, eigenvectors. All right, that we have already done. This is what we said, that for normal matrices we already have this, and for Hermitian matrices we had something special. And what was that? That the eigenvalues are always real, and we can choose the eigenvectors to be in Rn itself. So, we can choose. So, can choose U to be an orthogonal matrix and D as the eigenvalues of A times A transpose. Is that okay? That is more important. Understand it nicely. What I am trying to say? What we are saying is that I want my A to be U sigma V transpose. I want this A, fine. So, if I compute A times A transpose, this is a symmetric matrix, and therefore, by the theory that we have developed till now, we know that I can decompose it into U d U transpose, where U is unitary. Since it is Hermitian, so I can take U to be orthogonal. So, I have this is as orthogonal matrix. D is diagonal matrix, diagonal consisting of eigenvalues of A times A transpose. Is that okay? So, I can do this. So, the idea is to compute A transpose and get the vector U, get the matrix U and D. Is that okay? So, in the expansion, when I want my A to be U sigma V transpose, I know what U is. I can compute U as your eigenvectors coming from U, all right. So, in writing A as U sigma V transpose, U comes from eigenvectors of A times A transpose. Fine. Sigma also comes from this part that we have also seen. Fine. Now, let us compute from where do I get V or V transpose, whatever we want to talk of, from where do I get it. So, I want to now look at, so I wrote A as U d V transpose and we got A times A transpose. Now, let us compute A transpose A. So, what is A transpose A? A transpose A is now, A was m cross n. So, this is now my n cross n matrix for me. Fine. So, let us do that. So, it is U sigma V transpose whole transpose U sigma V transpose. This is same as V sigma transpose U transpose U sigma V transpose, which is same as V sigma transpose sigma V transpose. All right. So, you can see that now the matrix V, by the same argument, the matrix V appears as the columns of the matrix V. The matrix V has columns that are eigenvectors of A transpose A. All right. Again, note here very important that A transpose A is a symmetric matrix or Hermitian matrix, whatever you want to say. So, if A has real entries, A transpose A is a symmetric matrix, and this implies V can be chosen to be orthogonal matrix, and therefore, V transpose makes sense. I do not have to compute the inverse, I just write V transpose because V transpose is same as V inverse. Is that okay? So, when I want to write A as U sigma V transpose, A is m cross n, U comes from the spectral decomposition of A times A transpose. This V comes from a spectral decomposition of A transpose A. Fine. Sigma, understand, eigenvalues here they come from sigma sigma transpose, eigenvalues here they come from sigma transpose sigma. Fine. Is that okay? So, these are the two things that have to be careful, and I want this sigma for us, want sigma. I do not want sigma sigma transpose or sigma transpose sigma, I want sigma. That is more important for me. Fine. So, what we say is that this sigma, so look at this. So, what we are seeing here is that, note, fine, that sigma sigma transpose and sigma transpose sigma, they have same eigenvalues, same non-zero eigenvalues, I will say, same the non-zero eigenvalues are same and have the same multiplicity. Fine. The non-zero have the same. Fine. 0 may be there, 0 may not be there. The eigenvalue 0 may or may not appear, and this I will put it under a quote mark because it is m cross n. If m is not equal to n, then at least one of them will have 0 eigenvalue coming into play, because what we had seen was that the matrices AB and BA, they have same non-zero eigenvalue, same multiplicity, but there is a problem with adding extra zeros. This is what we had seen for our matrices AB and BA. All right, AB and BA, we had looked at that part. Fine. So, this is the same thing here. A is sigma, B is sigma transpose, AB and BA we are looking at. Fine. So, let us try to understand this by an example. Let me compute this with an example. Fine. So, example. So, I will take only one example. Let me define A as something easy, which is 2 1 1 2 1 minus 1. Let us compute A times A transpose. So, A times A transpose is 2 1 1 2 1 minus 1 times 2 1 1 2 1 minus 1. I hope I am correct. So, I do a lot of mistakes, all right. So, 4 plus 5 plus 1 is 6, 2 plus 1 is 4, 4 and minus 1, no, 2 plus 2, 4, 4 minus 1 is 3, yes indeed 3. It has to be symmetric, so it is 3, 1, 4 and then 6. This is what I get, fine. So, what I know is that I am supposed to write A transpose as, so let me write, otherwise I will always get confused as usual. So, A transpose for me is U, is it? No. Yeah. A transpose is U. I think I wrote here. So, A transpose is, no, A transpose A is V. So, A transpose is U. So, A transpose was U, sigma, sigma transpose U transpose, all right, fine. So, what I have here is U I can take. So, eigenvalues of this, so eigenpairs here are eigenpairs. Pairs are 6 plus 3 is 9 with 1 upon root 2, 1 1, this is 1. The other is 6 minus 3, that is 3, and 1 upon root 2, 1 minus 1. So, these are the two eigenpairs, and therefore, this implies that U is equal to 1 upon root 2, 1 upon root 2 corresponding from this part, and then 1 upon root 2 minus 1 upon root 2 coming from this part. Is that okay? So, I have got the matrix U, and sigma sigma transpose is nothing but 9003, all right, because A transpose, this is there because A transpose is U D U transpose, fine. So, therefore, D is this that you have got here. Let us compute A transpose A. A transpose A is 2 1 1 2 1 minus 1 times A 2 1 1 1 2 minus 1, which is equal to, multiply this by 2, 4 plus 1 is 5, 2 plus 2 is 4, 2 minus 1 is 1, I hope I am correct, I do not know, 1, 2 plus 2 is 4, 1 plus 4 is 5, minus 1, multiply this by 1, so just add, so it is 1 here, minus 1 here, and 1 plus 1 is 2. I hope I am correct, it is symmetrical, I hope it is correct, all right, fine. So, what we know is that the eigenvalues of AB and BA are same as far as the non-zero part is concerned. So, I already know that the eigenvalues of this matrix are 9 and 3. So, the eigenvalues here have to be 9 and 3, that is the first thing that we understand, fine. What about the third eigenvalue? This is a 2 cross 2 matrix, this is a 3 cross 3 matrix, so 0 has to be here. So, these are the three eigenvalues that I need to look at. Let us try to get those eigenvectors. So, if I see the eigenvectors, yes, I get it. So, you can check that A transpose A of 1 1 0 is 5 plus 4 is 9, it is 9 times 1 1 0, you can check that yourself, fine. Then I need to go the other way around. So, I want 3 to be then eigenvalue, 3 as an eigenvalue. So, 5 plus 4 is 3. So, 1 minus 1 has to come somehow. So, A transpose A times, I want something to be equal to 3 times the same number. So, I should get here. See, the idea is that this is a symmetric matrix, A transpose is symmetric. So, the eigenvectors have to be orthogonal, all right. So, this one eigenvector is already 1 1. So, I have to look at 1 minus 1 and then something, all right. So, I have to have 1 here, minus 1 here, 1 and minus 1 here, and something that you need to put. So, what should that be? Fine. So, since it is this, I would like to look at here. So, 5 minus 4 is 5 minus 4 is 1, I want 3. So, maybe I could put 2 here. So, let us check whether it is okay or not. So, 5 4 1 minus 4 minus 5 and 1 plus 1 and with 2 plus 2 minus 2 plus 4. So, it gives me 6 it gives me 4 minus, that is minus 3, and this is correct. Yeah. So, this is the one that I am looking at. So, I have this part, and then there will be one which will corresponding to 0. So, A transpose A times something should be 0 times something. So, this seems okay. I think 5 and 5 cancels out, 4 and this cancels out. So, it will be 1 minus 1 minus 1. All right. So, you can see that everything is nice. I hope it is correct, no? 1 minus 1 will give me 2 minus 1. Yeah. So, this is correct. Yeah. So, the eigenvectors for me, so what we are looking at is V. V will be coming from these of length 1 unit vectors, because I want V to be orthogonal. So, it will be 1 upon root 2, 1 upon root 2, 0. This will consist of the second one. So, this was 9. See, I have to keep the same order. 9 is here, 3 is here. So, I have to keep the same order. So, first I am looking at 9. The second is 3. 3 is nothing but 1 upon root 6 minus 1 upon root 6, 2 upon root 6 unit vector. And this is the last one, which is 1 upon root 3 minus 1 upon root 3 minus 1 upon root 3. All right. So, I have got your, as far as we are concerned, and here our sigma transpose sigma is 9 0 0 0 3 0 0 0 0. All right, this is what I have. So, we have got everything here nicely. Let us try to understand what we want. We wanted A to be equal to U sigma V transpose. All right, this is what we wanted. Fine. U is already there with us. Where was U? I wrote somewhere U. I wrote U here. This is my U. Fine. V is there, so I can just compute V transpose from here. So, I can get this also. Fine. Now, sigma is supposed to be a matrix of size U is 2 cross 2. So, this V sigma has to be 2 cross 3, because this is 3 cross 3. All right. So, the matrix multiplication tells me that sigma has to be 2 cross 3. So, just write this part, use these two ideas to write yourself, and it is sigma, not sigma square or sigma transpose. It is just sigma. It means that I am looking at a square root of that in some sense. Fine. So, recall that we had those ideas with us. So, what we want is they have to be a square root of 9, a square root of 3, and singular values we only allow what are called positive. All right. So, let me write that part also. So, what are singular values now? I will define what are singular values definition. Singular values of a matrix A, which is m cross n, are the eigenvalues of A transpose A oblique A transpose are the square root, positive square roots. All right, no negative, only positive square roots. Positive square root of the eigenvalues of this. Is that okay? Fine. So, I can have 0 sometimes, I may not have 0, it will depend on the rank. All right. So, here in this matrix A, the rank is 2. So, I have got exactly 2 of them which are non-zero, that is 9 and 3. If the rank was less, I would have got 0 as an eigenvalue, because of some result that for any symmetric matrix the rank is same as something, number of non-zero eigenvalues and things like that. Fine. So, let us do what is singular values. Singular values of a matrix A, which is a rectangular matrix, are the positive square root of the eigenvalues of this. So, here in this example, my singular values are the square root of 9, which is 3, the square root of 3, which is same as the square root of 3 itself. All right. So, these are the two things that I have. So, therefore, my matrix A, now I can write A, which was 2 1 1 1 2 minus 1, is nothing but U was this matrix. Now, the singular value will be 3. So, be careful, do not change the order. This corresponded to 9, this was corresponding to 3. So, I have to take care of 3 0 coming from this part. This is coming from 3. So, this corresponds to root 3, that is this. So, it is root 3 here for you. Fine. So, be careful. So, first column comes from this matrix multiplication. All right. This is what you have to be careful about. The last is 0 0. From the row point of view also, you can see here that 3 corresponds to the first one, that is 1 upon root 2, 1 upon root 2, 0. But now I have to look at the row, all right. See, I am looking at the row transformations now, because it is on the left. I am writing V. So, I have to write V transpose to make sense here. So, I have to write 1 upon root 2, 1 upon root 2, 0. Root 3 comes from 1 upon root 2, fine, sorry, 1 upon root 6, minus 1 upon root 6, 2 upon root 6, and 0 eigenvalue comes from 0, sorry, क्या यार गलती करता रहता हूँ इतना, 1 upon root 3, minus 1 upon root 3, minus 1 upon root 3. Is that okay? So, I have computed for you the matrix U, this is your U, this is your sigma, and this is your V transpose. Look at V and V transpose, this is what I have. Is that okay? So, you need to understand this and understand them in a very nice way, in the sense that when we do actual computations, I have the matrix of size A is m cross n, all right. The n could be very large as compared to n, or vice versa, whatever it is. So, what we are interested in trying to understand the largest eigenvalue in some sense, all right. So, you would like to say that which is the one which is more crucial, all right, which is the more important direction that I want to go to, all right. So, here this 3 comes from this part, and it also comes from something which is this part. Is that okay? So, these are the 2 parts in which I need to play around. Is that okay? If I want to look at the minimum, 0 is not allowed for me. So, I need to go through this direction. So, maybe this direction, sorry, this direction and this direction that I need to look at. Is that okay? So, for each of them you need to understand where do I need to play with. Is that okay? Fine. So, in your examples, in your theory part, everything looks okay, but when you look at applications, you have to be careful which rows and which columns need to be looked at. So, again, as I said, matrix multiplication is the one which comes to play. If I want the largest, this is the largest among the 2 singular values, 3 is larger than root 3. So, and this comes from the first one, and the corresponding entry is this from this side. So, these are the 2 things that I need to play around with, fine. Similarly, minus and so on. So, these ideas have lots of application when we look at what are called application in biosciences or biology and so on, where we are looking at that there is some drug that has come, you want to experiment and then find out things, or means how they behave on different people, what are the positives and what are negatives, also who is infected with what and so on, and percentage of infection. So, these vectors will give you which are the most important factors in which things are going to be localized. Again, I want you to be very careful in the sense that understand that these 2 vectors that I am looking at, fine. So, the vectors that I am looking at here, this vector, sorry, this vector and this vector, they are perpendicular. This vector, this vector, this vector are perpendicular. So, what you are trying to say is that you are trying to get what are called decomposition, all right, orthogonal decompositions in some sense. And orthogonal decompositions, what we saw was that they will always give you linearly independent things, fine, because any set of linearly independent vectors is linearly independent. So, you are able to decompose whatever issue you have in terms of these small ideas and then build up. Is that okay? So, what we will say is that I would like to end this course with the following idea, that we started with very simple ideas of solving system of linear equations. From there we saw that this idea can be understood from the point of view of vectors. So, we went to vector spaces. From vector spaces we could try to find out what happens for finite dimensional cases, what do I mean by basis and things like that. Once we have understood it, then we went to what are called linear transformation functions to say that every finite dimensional vector space is basically Rn over R or Cn over C, and then build on those ideas, understood matrix multiplication back again. We also showed that every linear transformation from one finite dimensional vector space to another finite dimensional vector space is basically comes from a matrix T of B comma B or T of A comma B, whatever you wanted to say. Then we went to eigenvalues, eigenvectors, and got all the decomposition that was required, all right. So, I would like you to keep track of all the things, all right, because they will come in the exam. Singular value decomposition will not come in the exam, but we will have questions about A transpose A and AA transpose, because they also come in the chapter on inner product spaces, where we looked at the not the actual solution, but the nearest solution, all right, a solution which is nearest to the given vector b. Is that okay? So, that is all. Thank you.